much. So welcome everybody. We're going to go through some training today on NMIS model creation and customization. It is the 21st of June here in the future in Australia. Our agenda today, we're going to run a quick overview of NMIS9, a bit of a recap on how it works, because there's some very important concepts for people who haven't sort of worked on this in the past. Let me just save this to my local drive. For some reason, something weird's going on. So NMIS9 overview, and we'll go through then how the models work and how we talk about SNMP, because ultimately modeling and how we collect data is all about data. So where do we get the data from? We get most data from SNMP, and we learn a lot about data from SNMP. So we're going to run through that, because even if you're using RESTful APIs to collect data and for modeling, you still have to, structure the data and so forth. So we'll talk through that. We'll talk about adding a new device. We'll talk about using the different types of modeling and the different structures that we use for modeling. And again, that goes back to what the data looks like. And then we'll go through the process of adding a system health section. We'll talk about device model plugins, and then we'll be talking about model policies and then some tools to actually help do all of this and make it possible.
Hello, everybody.
Hello, hello. So, message. So NMIS9 was introduced several years ago now June 2020. So it's actually 4 years old. There you go. It's going to go to kindy soon. And the high level architecture, and we're going to go to a slightly more detailed picture in a second, but the architecture is that you have nodes that you're talking to, so physical or logical devices. We call them, I've been calling them nodes for a long time. Don't know why, but I do. So nodes are something that logical or physical device, but it's something you talk to, it's something you manage. And then from that, you're talking SNMP, WMI, ICMP. You could be doing service monitoring, RESTful APIs, any number of things. And we have a bunch of pollers that handle that. So the poller, and that would be a worker thread, is a poller. It's collecting data and it puts data into NMIS, and that's multi-threaded. Then we abstract everything through policy configuration and models. And then, all of that stored into database. We use MongoDB for various reasons, which we'll cover in a second. And then, on top of that, we built a full object model. NMIS 8 was great. NMIS9, we liked, as we said here, keep the best bits, make it better. So we kept what we liked about NMIS 8, and then we kept what we'd learned about, these things, and then we sort of made it better. And one of the big goals for NMIS9 was to make the data available across multiple servers. So that was really, really important. These slides will also be available. I think I sent them to the attached on this actual meeting invite. If you don't have a copy, please let me know and I'll send you the PDF. Cool. So why did we select MongoDB? MongoDB was, at the time that we made this choice, it was absolutely the right choice. And to be honest, today, it would still probably be our choice for its multi-purpose, jack of all trades database, in essence of a document store database, or what we refer to as NoSQL, or sometimes big data. And you can just store lots and lots and lots of things in it, and then you can create indexes, and the indexes are all in memory, so it's extremely fast for certain things. The database, we're still very happy, and we still love MongoDB, and it's now got things like in the newer versions or the more recent versions of MongoDB, there's now column store and time series support and a whole bunch of other features that we're not leveraging yet. That's for the future of our products. So what are the important concepts that we have for NMIS9? That's really, really critical to understand. So the architecture, how the jobs are processed, configuration of models, and data structures. We'll run through this quickly. So NMIS9 plus the OP modules. So basically the blue stuff is our NMIS9. Starting at the bottom, we have those nodes. We have a daemon, and that daemon polls things and collects things. So all the work is sort of done through that daemon. Then we put things into the abstraction. So it's really important. Everything we do is through an abstraction. It's through the object model. This is pretty normal. But when you don't talk to the database directly, you talk through an abstraction. Again, very important programming concept, but it means that you have consistent access to the database. You're always going through and that things are verified. It also means conceptually that we could change out a database system underneath and no one would know. You could just swap out a database for a different one. And then the abstraction then is responsible for persisting data to a database or to the disk. So it might be talking to files, it might be talking to logs, whatever's going on, the abstractions handle all of that. Now the user interface, users come into the user interface, and of course we have the CGI user for NMIS, interface for NMIS9, and we also have a CLI interface. So the user interface is both command line as well as through the GUI, the graphical user interface, and you can ask the system to do things. You can use buttons in the GUI, or you can go to the command line and do things. Now, sitting on the right of that, we sort of have a parallel architecture, and again, very abbreviated architecture for our what we call our OP Mojo stack. But at the the back end system has an internal API and OP modules. So we have this back end system that has all of the object models for all the different things, and then it talks to the database, or it talks to NMIS. So if it needs data out of NMIS, it talks to the NMIS APIs natively, or if it needs to talk to the database for its own data, then it would talk to the database directly, always through those abstractions. Then we have this concept called OP data, which is essentially an internal API for everything where our apps can talk across each other. So when you're in OP charts and you're showing data from OP events, that's made possible by using OP data. There's again a layer of abstraction there that makes that possible. So some of the front end talks through OP data, some of the front end talks directly to the OP modules, and then now we have those front end components like that we refer to as OMK forms, OMK view, OMK grid. We use Backbone, we use, and then that's where we offer our public API. And this is a real summary. Focus here is NMIS9. There's a whole lot of other stuff in our stack, but that's the interactions. That's how we interact with NMIS9 from the OP modules as well. So job processing, one of my favorite things to say is pre-fork worker pool. Don't know why, it just rolls off the tongue really nicely. So NMIS9 uses this concept, and we use this concept across our products in general. It's a very good pattern. It's how you learn to make things scale very, very well. So we have a set of workers, and in this case, it's an NMIS9 worker, and there's a scheduler, and then you ask the scheduler to get work done, and it goes into a queue, and then the workers look at the queue, and then the scheduler works with the workers, and then a worker picks up some work and does the work, and then says it's available for more work. So the way you scale NMIS is by adding more workers. So if you need NMIS to do more work, you add another worker, right? And then of course you have to have enough CPU, memory, and storage to make that worker have enough resources. So that's how you scale, right? So if you don't have enough memory or CPU, you need to reduce the number of workers. If you don't have enough workers to keep up with your nodes, you need to reduce the number of nodes or add more workers. This is how you manage the performance of a server. Same thing would work with other systems. Almost all other systems. Depending how much work you give it, you need to have the appropriate amount of resources to support that work. So we do that through our workers. They're not in a union either, so they don't have any rights. Just robots. So NMIS9 configuration of models. So basically, we have it's a really important concept. We have this concept called default. So you have a config default or conf default, and you have models default. When we do a patch or do an upgrade of NMIS9, we will change those files, and because they're the default configuration. So if you're not customizing your system, and often when you install an NMIS9 system, you don't have to make many changes. If you choose to, then you would have those in the conf directory, or you would take the model from the default directory and put it in the custom directory. And we did this for various reasons, but basically it means that things that the models that you're not modifying for yourself, they get automatically updated and maintained and supported by us. And then same thing with your config. If we make sort of minor feature change in NMIS9 to some system or something or other, and you're using those default files, then you'll automatically get that upgrade. You don't have to think about it. If you've customized your system and you've modified how you want the system to work, then you need to think through how you want that feature to use or what that capability is, and then you would just turn that feature on or off, and you decide by using the conf. We also support a conf.d, so you can have config fragments. So you don't have to have a single file with your NMIS conf in it. You can actually have 10 small files, and then NMIS will just merge them all together and treat them as one. And it's the conf.d are loaded last, so they override what's in the conf file. So that config hierarchy is really important, and you've got to maintain it. And then we also keep caching. So the modeling system also looks for files that are changing, and then it updates them and changes them as necessary. Inside the database, there's a relational model in just a second. But basically, the main structure of the database are the following collections of things. So we have events, we have inventory, we have what's called latest data, and then we have nodes, op status, queue, and status. And these are all of the main collections inside the Mongo database. There is another set of collections called the timed data. And then, so the timed data is the last 24 hours of performance data in the database. And then but your latest data is all the current performance data for the last thing polled. So that's why it's called latest data. So it changes. So inventory doesn't change very often, whereas latest data changes all the time. So these are the architecture of the system is that you don't have to replicate all the data all the time. You just replicate the data that changes. So this is what the structure looks like. So you have a node in the middle, and a node has an ID, and that ID is the database ID, and this is very important. And then we have a user assigned UUID, and then we have obviously we have a name for the node, and then you have a cluster ID. So the cluster ID is the whatever's polling and collecting the data for that node is the cluster ID of that poller. So if you're asking this node to be polled on that poller over there, then that data for all that node will have that cluster ID. And you always know that when I'm looking at this data, wherever other server it ends up on, that the data was sourced and came from that poller over there with that cluster ID. So that cluster ID is carried through everywhere, and it's part of the referential integrity of the system. And so your UUID is then used, it's user assigned. This means that we assign a UUID and we give a node UUIDs automatically. If you wanted to, you could manually assign the UUIDs and we would honor those. And this is really useful for when you're integrating with something like ServiceNow. So you can have the same ServiceNow UUID in ServiceNow, for example, as well as inside, our solution. That's nice. It's really, really nice for lots of customers. But you don't have to. We just automatically assign a UUID if you don't want to manage them yourself. For those who don't know, a UUID is a universally unique identifier. Conceptually, mathematically, it's like 1 in a billion, might be more of likely to get a conflict. I mean, it's pretty remote. It might be 1 in a trillion these days, but it's pretty remote that you'll get a conflict of a UUID. It conceptually could happen, and I think I may have even seen it once in my life. So the inventory then gets broken down, and as we collect data and we put data in, and this is all very important for the modeling sort of thing. So as you model things, there's going to be an inventory object created for that. And so you have this structure where you have the ID of an object, you have the node UUID, you have an expire. So we never delete records, we let them expire, and they kind of just get aged out and disappear magically with the magic of Mongo. And that means that we save performance on the database. So there's a different way to, you don't sort of go and have to consciously go and delete all these records. They age out over time. And we've been using, again, we use that across many of our products, and it's a very nice feature of MongoDB. Then you have the concept that you're collecting for. So the concept would be, for example, interface, CDP, BGP, whatever it might be, something MPLS, might be temperature, whatever it might be, that's your concept. And then you have the actual data, and then the path, how you get there, and then where the thing is stored. So that's the higher level inventory structure, and you actually interact with that using modeling. So all of that's taken care of you magically. The object models and NMIS just handle all of that and put the data away for you. There's a bunch of notes there. If you've come from NMIS 8 and you sort of trying to understand how it works, we've got a nice page there of great information about sort of the differences and what you have to do. But there's a bit of a summary, and we've already covered this. They've covered the details of this. But especially if you come from NMIS 8, you probably want to pay attention on that particular page. So, all right, we'll dive straight into modeling. So here's the reference material for modeling. There's some great references on the wiki page, that have been there for a long time, and we keep them up to date. The training that we're actually doing now, there's an older version of the training here. Most of it's still relevant, but it's the NMIS 8 modeling. You know, we're sort of, the modeling hasn't really changed. There's only like 1 or 2 things that are different in the NMIS 9 models. They're actually forwards and backwards compatible. Obviously, plugins are not compatible. But there's just some nice reference links for you, and then we're going to go through some of the details of some of these, and you'll see these pages specifically referenced in the rest of the material. But there's just a quick list of the references. So why does NMIS have a modeling system? So what's really important about data is that, and about humans, is humans can't agree on what to call something. So, you know, if someone decides to call it a CPU and someone decides to call it a processor, they're both right, and they can both be right. There's nothing wrong with that. However, we need to collect that processor information. We need to collect that CPU information, and we want to store it in a consistent way. And we've decided to call it CPU. So whatever we do, we use the modeling system to collect the thing that the vendor has called it. So the vendor's called it a processor. Another vendor called it CPU. We use modeling to collect the data and then normalize it into the database. And that means we can do lots of cool things, have more consistent data models inside NMIS. So that's what the modeling system's really there to deliver. And the modeling system also helps us to abstract away from, you know, concepts. So you use the modeling system to describe the data and how it's going to look. So this goes back to the model view controller sort of concept. So the modeling system in NMIS is the modeling part, and there's also a view component to it as well. And you know, the controller is the NMIS engine doing the work to go get stuff, and there's a GUI component to that as well. But basically, you can use the system if you needed to use netconf or RESTful APIs or something else. You could use the modeling to describe what the data is going to look like and how it's going to function, and then you would use a plugin to go talk the crazy protocol, you know, that you need to talk, whatever that might be, collect the data and put it back into NMIS. You know, we've had quite a few customers, and it's a really common problem with various platforms around the world, but they'll have really good SNMP support, but they may not have good SNMP support for certain things that you might need to collect. You know, we might need to you know, use a RESTful API to get some data. We might need to use CLI, you know, and using opconfig, you could collect the result of a show command on a Cisco router, or you could go into the proc files on a Linux file system and grab out really detailed data that you might want to get modeled into NMIS for whatever reason. So that's what the modeling system's there for. That's what it exists for. It's a whole bunch of really cool functionality that you can use it for. So what are the types of files that we have? The main file is the model file. That's sort of the bootstrap for how the system sort of works. Then you have a bunch of common files. They all start with the keyword common, and then we obviously have some graph files, and then we have model files. And we'll go through in a second in a bit more detail, but that's the main types of files that you're dealing with. And then very, very rarely do you ever have to deal with the enterprise file. The enterprise is when you're adding a whole new vendor. We've probably got most of the vendors covered, you know, but I'm sure new vendors keep emerging. I don't know how many in the time that NMIS has been running, even the time that I've been working with Opmantec and now First Wave, you know, vendors have come and gone, and they've appeared in the enterprise MIB. So anyway, there's the enterprises is how we track vendors and so forth. So how does modeling work? So the first thing that happens is that when the system's talking to a device, it collects the sys description and the sys object ID. And from that sys object ID, it determines the vendor by looking at the enterprise's file. So we go and extract what's called the enterprise OID, and then we look that number up inside the enterprise.nmis, and we find out that 9 is Cisco. Right, and that's a common one. They got a number really, really early, and that's cool. And then we can also use auto discovery. So now we know that vendor, that this device is from Cisco or from Juniper or from you know, Palo Alto or whoever. Right, we now know where the device is from. So now what we do is that we look at the sys description and we do a pattern match on the sys description, and now we find and we look up in the model NMIS. We look at the vendor list. We match in order. Once we've matched one, we go, great, I found a model that matches this device. And now we load that model, right? So the model.nmis is about auto discovering and auto selecting the right model for the right device. So if you have a Cisco, and it's very, very subtle, Cisco and Juniper and all of these big vendors, Palo Alto and Fortinet are too small for this at the moment. They probably only have one operating system, but most larger vendors that have been around for a while have many, many operating systems which are subtly different. They might support a lot of the same MIBs, but they're not the same devices and they operate a little bit differently. And so switches and routers operate slightly differently, even though they both run iOS. But now you've got the newer versions of Cisco iOS, iOS XR, for example, and the numbering's a bit crazy and a bit different. So that's what the modeling system is there for. So you pick a different model for a different, like for a Cisco ASR versus a Cisco ISR. They might have different things they're capable of. So you want to load the right model for the right product. More extreme would be, a server and a router have very different things you want to collect. You don't care about storage so much on a router. It's obviously very important on a server. So, you want to identify what the thing is best you can, and then now you load the model to collect that data. And then we get that data from the NMIS9 database. Excellent. So let's go through that in a little bit more detail. So the first thing that happens is that we collect from the device the sys description, the sys object ID. So NMIS does an SNMP get to the router and gets back these two bits of information. Here is your enterprise sys object ID, and that number there, the large number after 41 is the enterprise ID. This one is Microsoft. So this is telling us that this is a Microsoft thing, and it's this object ID. So now in the enterprise for 311, we have the OID and we have the enterprise name called Microsoft. Then in the model file, we have Microsoft. So we're matching, and now we've matched that. And then we go down and we're looking for Windows. This is actually a regular expression on the right. So we're matching that regular expression, comparing it. And then we get to, we find that Windows version 6.1 matched, and that's Windows 2008. So now we know that this device will support the Windows 2008 model, and now we load that model and use that model. So that's how that step works. Once we've loaded that, we now load all the common data. So we go to that model file and we load all of the common things. So common is like an include or a requires or use, depending on which language you like. So you use the common to have modularity in the modeling. So for example, a lot of the stuff with servers can be commonly used, and across Windows devices can be commonly used. There's a set of common models for a bunch of Cisco concepts that all Cisco products use. So there's a lot of great reuse and modularity in the modeling system, and that comes from the common system. And then we have all those base structures, system, interface, storage, device, etc., and that's all in the model file itself. So now NMIS is now ready to go and collect data from that device. So we've just sort of touched on this, but this is the main structure of a model. So you have a node, it then has the common section, it has the system section. So typically, this is a good one for a Windows box, but you typically have your node health section, a MIB2IP, host resources, Windows, modem, temperature, power, and then you have an interface section, because interfaces are very special. We're still modeled in this, we still handle them, but there's so many exceptions in interfacing. We do have special handling of interfaces in NMIS just to handle all of the crazy things that vendors do with interfaces, but you can influence all of that through the modeling system. And then under interfaces, we have input, output, octets, packets HC, etc. Then we have storage and system health, and we're going to go through system health. It's the big way that we do extending and adding more things to models. So most of the modeling now done for devices is done under system health. So then here's a bunch of standard common models, and there are a set that are probably deprecated now, just self-deprecated. They're not self-deprecating, but they've, no one uses calls, no one puts phones really into Cisco routers anymore. They probably don't put modems into Cisco routers anymore either. I'm sure somewhere in the world that's still happening, but they're still supported in the system, but hardly used. And you've got Cisco class-based QoS, input and output, and then all these other things are really, really, truly common multi-vendor. So database, event, heading, stats, summary, and threshold. They're your main sort of top-level sections that you would have. So if you're doing thresholding, you could put the threshold in the device model itself, or you would go to the threshold model and modify that one. So if you're doing, you might not need to touch any other models, but if you're just tuning the thresholds in your system, you'd take that common threshold out of the model's default, and you pop it into model's custom, and you'd start tuning your thresholds. So let's talk about the process for modeling a device. And this, I always find this really funny because people say, can I, do this modeling? Sure. I said, what are you trying to do? So what's really important is, you have to collect information from a device, right? It sounds kind of obvious, but you have to have, a way to collect information from a device. You need to have a goal for that modeling. So why are you wanting to collect this information from the device? So are you wanting to track the temperature? Are you wanting to detect if a process has failed? Are you wanting to look at a fan failure? Like, what is the goal for the modeling? What is the outcome you're trying to achieve, right? Now, is there device instrumentation in the device for that modeling? Because I've had customers come to me over the years and say, well, Cisco's got some great QoS features. We'd really love to get those QoS features in other brands of routers. And I go, well, that'd be great, but I can't do that because I don't manufacture those routers. So all NMIS can do is talk to the instrumentation that exists in devices. We can't, except for a Linux box, we can make instrumentation on a Linux box, and anyone can. But on a vendor's device, a hardware device with a closed operating system, we can't extend that, and add more instrumentation. So there has to be, if I want to collect that temperature sensor from that device, the device has to support temperature sensors, right? Sounds obvious, but I've got to have the device instrumentation. Is the instrumentation relevant? Does it work? Like, is it give you the right data? Is it accurate? Like, there's a bunch of things about that instrumentation that are really important. And now, assuming that I'm using SNMP, because most of the time you're going to be using SNMP for networking vendors, and you could be using RESTful APIs, but you need the MIBs so that you can interpret the data. If you're using some sort of RESTful API, you need to have some understanding of how that API works. That would be your API documentation. I just realized I didn't bring myself a bottle of water to my study. The supported MIBs for the device will tell you how to decode the MIB, how to understand the device, and we're going to do a little bit of that in a second. And it's really, really good idea to get to sort of answer a lot of these questions. You can get an SNMP walk of the device with the MIBs loaded, and probably one without the MIBs loaded. And then you can review the MIB and that SNMP walk and kind of understand how the device works and if the instrumentation is useful. And then you might even want to collect a walk a couple of hours apart to see if the instrumentation changes, because sometimes people have wanted some MIB and the vendors told them this is the MIB you use, and we've gone through the modeling process, and the customer comes back and says, oh, that MIB, that modeling it doesn't work, it's just always 0. And it turns out it's actually just the vendor's not doing anything with that instrumentation, and they documented it's on their website that has the temperature or whatever it might be. It just doesn't work. There's a bug in the actual operating system of the vendor's device, right? And we do find these more often than you'd think. So device modeling checklist link down the bottom. So let's decode an SNMP MIB. So I found a nice little example from an Emerson Power Systems device years ago. It's a nice little short MIB. There's almost nothing in it. There's very little data in it, but very useful data, but not too much in it. So here we have our Emerson MIB. It looks like at some point I've accidentally copied some data here or got bumped a mouse. So that looks like it's there. Let's put that back. Okay. So in this OID here, you've got the name, the Emerson Network Power. You've got this thing. So you're looking at this SNMP walk, and you don't know what these numbers are. So you're sort of looking at it and you're going, what does that mean? Well, I need to interpret that somehow. So we need to get the MIBs. Where do I get the MIBs from? Well, I can see that this vendor here, 6302. So I can actually go and Google that. And if I Google that number, so whenever I see this phrase here, SNMP Enterprises, that means that's the OID for it. So I can go build up a nice string. I can go Google that, and it reveals pretty quickly through the magic of Google that it's Emerson Energy Systems. A little bit more Googling and hunting around, I found the MIB for it, EES Power MIB. Emerson were great. You know, SNMP being an open protocol, they made their MIBs publicly available, easy to find. Some of those vendors out there are less nice, especially the telco vendors tend not to be so friendly with MIBs, and sometimes you've got to sign NDAs or whatever. But, you know, you've got to go get the MIB file. You might have to ask the vendor for a copy of the MIB file if you can't find it online. And then, you know, a little bit of documentation, and that was all very useful. So I was able to figure out this MIB was useful. So now we know, we see some values here. We don't know what they are. We've got a MIB file that we can look at. So what do we do now? So this is the MIB tree. So conceptually, MIBs, and a very important point, which I should have started with before, mentioned before, SNMP is the Simple Network Management Protocol. The protocol is a simple network management protocol. I get data, I receive data, right? So I ask for data and it sends me data back. Very simple. The data I'm asking for is stored in the device, however the vendor decides to store it, but it's represented in, when we ask for the device, it's represented in the format of an OID and a value, name value pair, where the name of the device, the name of the data is an OID. I decode the OID through the MIB, and the OID is a unique thing. It's used widely across the IETF. So these are used also, MIBs are not just used in SNMP, they're used in other places. For example, X509 and X400 use MIBs for data descriptions things. So that's directories and email, right? X400 and X509. So X509 certificates, sorry, X500 is directories. So anyway, you've got all of these different, you're using OIDs all over the place. And in MIBs, they're describing the data, and that's what they're used for in other places. So the MIB is telling us that structure of the data, and it's represented as a tree. So you start at the top, and the root of the tree is ISO, then org, then Department of Defense, DOD, because it came from ARPA, then the internet, and then private, and then enterprises, and then Emerson. Now we're into the enterprise part of the MIB, and now we're in the global part. That's their naming. So now Emerson control everything after their number here, 6302. And we come to the power MIB, and then we ended up in the system, and we ended up finding out that those three variables that we're interested in are voltage, current, and used capacity. They're very interesting things for us that we want to understand. So now I can go into the MIB and I can look up what those objects mean. So now this is the actual MIB, the structure of the MIB. MIBs are written in ASN1 format. ASN1 is a data description language, again, used widely across all sorts of different things, probably most famously in MIBs. But you can compile, it's a language that you can compile. So if you're describing data, you could describe it using ASN1. So now we get to that system part of the MIB. That's the one we're really interested in. And it tells us that we have this object called system voltage, and it tells us that, and this is actually a really, really good MIB. They're not always this nice, but it tells us that the data is the system voltage stored as millivolts, including positive or negative sign. And then if it's got that value, it's an invalid value. So it's telling us how it does error handling. This is an excellent MIB, right? Not all MIBs are this good, but this is nice. And it's very brief and very easy to understand. And also it's a very simple concept, right? So, but it's telling us the unit. So now we know it's millivolts, milliamps, and percentage. So, and again, that's very important. And it's also telling us that it's represented as an integer, which means it's a gauge. So we're going to talk about gauges and counters in a minute, but you know, this is going to be a gauge because it's stored as an integer, not as a counter of some description. So again, that's important. So it says when I'm looking at a gauge, that's the value. I don't need to do any other maths on it. That's the value as I see it. That is the value of that measure. So now we've decoded the MIB. Now we've figured out that I've got something useful. I can do something with that. And let's go have a look. The next step. So what are the steps to do a new model? So we've actually got a tool now that kind of automates a whole bunch of this for you, but it is important to sort of run through what those steps are. The tool actually does some of the steps for you and prints out some nice stuff on the screen to help, and then you can sort of accelerate it. But, you know, basically you need to get the sys, you know, you've got to go get the sys description and the sys object ID. So getting an SNMP walk, you've got to go make sure that you've got some information from the device. Does it actually talk things? We've had some less than useful devices over time that, very minimal information. So it's just so the vendor's marketing team can write, we support SNMP, but the actual reality was it was very ineffectual. But, that's only been 1 or 2 vendors out of the thousands and thousands that use SNMP. So we get an SNMP sys description, sys object, to make sure it's useful and can we do something with it. Do we actually have an enterprise number already? So we go and check that. If not, we would go and add an entry to the enterprise NMIS. We'd then add an entry to the model.nmis. And then now we would decide on a new name for the model. So you might take an existing model to start with. So for example, model default, and then you would copy that and then you would update the system section of that model. This would be the manual steps that you'd be doing with the file. So let's go through those steps. So here's first step, add an entry to the enterprise NMIS. So you'd open that file, you would copy it to the conf directory, and then you would add your own NMIS vendors. Very unusual to have to add a new vendor. Very unusual, still happens randomly. Add an entry to model.nmis. So now I would add the entry for, whatever it is. My match from sys description would be device foobar, and then I'm going to have the model name, whatever I decided to name the model. Now I'm going to edit the system section. So I'm going to go in, I'm going to update the node type, the node vendor, and the node model to be correct so that they're all the same. So now I've got the base modeling done and I've got a new file I can use. So here's a real example. Turns out that Sun Microsystems is OID 42, which is somewhat poetic. For those who are under 40 and don't know who Sun Microsystems is, they basically gave birth to a whole bunch of stuff that you take granted for. But big proponent of open systems and open Unix. They had their own version of Unix, and there's still a bunch of Sun Microsystem stuff out there. Oracle bought them a long time ago and kind of kept them going. But Sun Microsystems were huge up until the noughties, I guess, and banks, huge in banks and service providers. So Sun Microsystems OID 42, very early in the game, and we would have an enterprise section here, enterprise Sun Microsystems OID 42. Then we would have a section called Sun Microsystems, and then I would have the order would be 10, and then I'd have Sun Solaris, that's the model that we created at the time, and then I would match Sol, Sun SNMP, or Sunos. And in the system, I would go and change this to be Sun Microsystems and the Sun Solaris to match the file name. Right, so I've got a file name called Sun Solaris, so I'm matching the node model to that name. This matches this. Cool. So the other option is if I was using, when you got to a certain version of Sunos, they actually just started using the NetSNMP agent. So then you could actually just go and add it to the NetSNMP vendor, and you could just have the newer Sun Microsystems boxes would actually just use the NetSNMP. So you could just go and tell NMIS to, if it's a Sunos box, it's a newer Sunos box, go use NetSNMP. Great. So now you get all the same data and you get it up to date. So now to do all of this, and we'll go do this on one of the servers. Just bring up a clean screen. But basically, to do all this automated today, you would have your model tool. You would point that model tool at a Cisco device. So we have a Cisco device here called New Asgard. I'm going to create a new model called Cisco Router Auto, and it's going to be called, I'm going to exclude, I don't want to deal with the concepts called Windows or TCP. I'm comfortable, that's pretty common. If you were doing some other device, you might want to include those things, but in this case, you don't. So let's go have a look at Polo. We'll go into our model custom file. There's probably one here that I made earlier. No, there's not. That's great. So let's go make one. Here's a command I prepared earlier. There's some schema errors here. That's because we've got some things we need to fix up, but that's schema errors as part of what the model tool helps you with. And so now it's automatically generated us a thing, and we'll do the debug in a second because some people might have some questions. So I'll show you how the debug on, and we'll have a look back through the results. But basically what the tool has done is it loaded all of the models that existed in the models default. It then looked through all of those models and found all the different things that it was possible to ask a device, over 400 different things that I can ask a device about. and then it goes and tries every single one of those MIBs against that device we've given it. The device must exist in NMIS, so you must have loaded the device into NMIS already, so it knows how it's got all the credentials and all the necessary information are all configured in NMIS. And the model tool then goes through all of those OIDs and all of those MIBs and everything and says, what do I add to this device? What should I add or what shouldn't I add? So here we see that it decided to add a lot of Windows system stuff. That's because of that model's not so, should be done differently. So that's why we exclude the Windows system thing. But you can see here it's now picked up Cisco Neighbor, Cisco Memory, it does LLDP, it does Cisco NetFlow, does Cisco Asset, does the power, does memory, does CPU, so forth, right? So it's figured all of these things out automatically, and then it's excluded them, and then it's written the model for us. And just to show, so here's the model generated by me just now. So if I was taking if someone sent me a new Cisco device or a new Juniper device or any mainstream vendor, Palo Alto, F5, whatever, I could just try an existing model first that I already have. And if I wasn't sure, I could run a model tool to have it generate one for me automatically. And I've actually used this tool in the last couple of years to improve our models, right? So it's a bit of self-referential stuff, right? So when you write a system that you can then use to help make the system better, that's kind of cool. That's what, it's computer sciencey stuff. That's cool. So, you can use the model tool to actually improve the modeling. So we've done that in the past and updated models and put those back out for everyone else to have access to. But let's have a quick look at this model in Vi, because everyone loves to use Vi. And so here you now see all the common things loaded, and it's got lots of them, and it's got the standard. So we do, the model tool takes a default model, just the way we described before. It takes a template model and then adds things to that. So it does a sort of a base model that it uses, which is the default V2. And then here's the interface section, and we're really just looking, oops, that wasn't what I meant to do. Oh, sorry, that was a terminal feature. Apparently Command D splits your screen, and I was looking for Control D. I'm just looking down for the sections. So there's the interface bit. There's the sort of the basic section. And then now we come into node model, Cisco router auto generated by model discovery, node type generic. So you change that around. You'd want to tune this node graph. We'll cover that off in a minute. It's figured out the MIB2 IP is useful. It works. It's supported. It's got the standard one. And then here's all the sections. So it's added all the common things, and then it's going to load from those common things these other objects, right? So now magically we've now got a model that supports that Cisco device, and we could go use that model if we wanted to. If we wanted this to become the default, we'd have to go copy files around and do other things, but this is a model generated automatically by the tool. So that's your best bet. That is your best bet for if you've got to do a new model. That's where I would start. We've just gone through the theory behind what you have to do and the steps that you have to do. The model tool is going to accelerate that massively. The team will have to do some work. There are some schema errors here. It looks like some recent modeling hasn't been quite so correct. So we've got to go fix up some of these. Just go and look at some of these things and find out, why is the structure right and so forth. So it actually does a schema comparison and looks for errors. So this model I import looks like it might have something going on. And so you can actually use it to check your existing models, and you can use it to verify if there's any. So for example, a graph type has an incorrect path. So someone's put an object. So it does a syntax check, right? So it does a sort of a language check as well. And it's got tells you if things are in the wrong path and so forth. So very handy tool. Right, moving right along. So we're going to add a new section to the node health, new metric to node health. This would be a standard thing that you would do. So we're going to just go through that process and talk through, how it works. I did this modeling a long time ago, so it's already present in NMIS for years, but it's sort of, this is how you discover new things and find new things and research them as well. So it would be really useful if I was monitoring a router to know how many routes that the router routed. So, I could monitor that and raise thresholds if it changed or do anything interesting. So how could we do that? So you could go hunting and Googling, and then quickly you find out there's a couple of different MIBs available: IP CIDR route number and INET CIDR route number. So that the two objects for those things are these two OIDs here, and you can see they're from the same MIB. And this is not that uncommon that someone releases a MIB and then someone else. This is the standards process. So someone says that's great, but I'd like to do this other thing with it. So they add another one in. So now there's two possible OIDs that we could use to collect this data. How do we now go from understanding which one of these is the right one to use? Could be either. So I'm a bit of a SNMP nerd and have been for a long time. So I've just collected over the years a bunch of different MIBs. So my way of doing research is to just go grep things in that directory. So I found out very quickly that IP CIDR route number was widely supported, with lots of different devices. The INET's CIDR route number is also supported by many vendors, and probably better supported now, maybe today, but this is incredibly well supported by most vendors for the IP CIDR route number. So that's one we decided to go for in this example. So we've done that research. That's how I did the research, or detective work. So you can Google this, right? So if you're going to work with a specific vendor, you could just go and get the device and do an SNMP get, and then go look at the MIB result, and then go run a show IP route or whatever the appropriate command is on that device. Does the information match, right? That would be a bit more of a hands-on way. But you could also just collect both objects. NMIS handles those. They're not SNMP errors. They're sort of dealt with by the system automatically. They're errors, but they're not errors we worry about. So I've decided now we've got to make some implementation decisions. So we're going to call the metric, because it's called IP CIDR route number or INET CIDR route number. We're going to just call it metric route number. That's a good thing. Makes sense to enough people. It's called route number. So the OID we're going to use is this OID here, and the graph will be called route number. So there's my decisions. So the MIB name is this, and then these are the different decisions I've made. So now we need to make the following changes. We're going to edit the model Cisco router, which is our, probably had the most modifications to it over time. And then we're going to add an entry to common heading, which you don't need to do an NMIS9 anymore. You'd add that to the graph. And then you do an entry into NMIS MIBs, which we'll talk about in a second. And then, we create a graph called IP route number. So you'd add the heading now in the graph directly. So the first step that we go into the Cisco router model, and we decided at the time, or I decided at the time, to add this to Node Health. I've since moved this out to its own route number section, separately, but that's okay. Still all works. It still applies. So we've called the thing route number, and I'm going to use the OID CIDR route number. Now the third entry here, add to the MIBs, NMIS MIBs. If you want to use a name here, you must have an entry in the MIBs, NMIS MIBs.oid, which is just a lookup table. This name is this OID. What's really important is SNMP only uses OIDs to communicate. It doesn't use names. So SNMP is always saying the name value pair. It says, give me these objects. It's always using an OID and sending an OID. So SNMP is always using an OID. We humans, we need names, because we don't, long strings of numbers don't mean much to us. They're not actually that meaningful, but IP CIDR route number means something. So that's more useful to us. So this is a lookup system that we have this loaded. So you compile the MIBs, you generate this list, and that's what we've done in the past. So you can just add one in there, or you could actually, and it's shown later in one of the examples, you could just put the OID directly into there and not worry about using the NMIS MIBs, which I think I just described here. Apologies, I should have just gone to the next page. So there's an example of doing that. So now I would create a new graph. So the graph is very simple. It's a gauge. I don't have to do much with it. I'm not too worried. I'm going to do a maximum, because that's always nice. I want to have a maximum. So I'm looking at a longer term. I've got the max. So now I'm going to say, go get route number out of the database. We're going to put it in a variable called routes. I'm going to have a line called routes. It's the number of routes. I'm going to give it a color. So this is doing a graph. Now, when you're doing these graphs, you're basically using the system underneath NMIS that we use for the performance data is RRD tool. It's a very, very powerful performance database that's been around for a really long time. It's probably getting, it's difficult to replace because it has a lot of functionality. Not all performance databases do what RRD tool does, and this is really just important to understand. So RRD tool lets you store the data, maintain the data, keep it up to date, and has all the functions that you would need. It's feature, I mean, people keep adding features to it, but it's essentially been feature complete for 15 years. I mean, people add more capabilities to it. It's got a whole bunch of mathematical functions, does cool things, and that's really the point. It's also got this system using reverse Polish notation, which I can go and ask to get data out, and I can perform maths on it. Now, reverse Polish notation is about as close as you can get, well, pretty close to assembly language, and it works the way the old-fashioned calculators used to work. So I put a value on, and I put another value on, and then I put an operation on. So if I want to add two numbers together, I push something to the stack, I push something else to the stack, and then I tell the system to add them. So it's really, 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 really fast, obscenely fast for doing these kinds of operations, right? It has been optimized so much over time. It's written in C. It's just fast. So you are getting data out of the database and performing maths on it, doing transformations on the data at the same time. It's very difficult to describe how much performance you need to get this done and how you make it scale. So RRD solves that problem. It has solved it for a really long time. Other vendors now, other open source projects have new solutions for this and how to solve them, and they often split the problem so the database doesn't do any maths and the front end does all the maths, and that's not right or wrong. There's just different ways to solve the problem. RRD gives you, the two components, the way to put the data in and the way to get the data out. And it works. We like it. We also put performance data into MongoDB, which gives us more flexibility, but we don't have the history stored in there. And that's quite intentionally because MongoDB, doing the way we do it doesn't scale so well. We would want to use the performance database at some point in the future. So now I've defined a small graph. I've been using these expressions here are basically RRD tool expressions, and I'm using those directly. So those instructions are just being passed through to RRD tool and run. So if you want more of an information about RRD tool, there's more information you can get there. It is a pretty powerful system. You interact with it most of the time when you're doing a graph, a simple graph like this route one. You would just take an existing graph and modify it. Most people who've done this, don't really have too much trouble. You do see we've got a small graph and a standard graph. In the case of this particular one, they're the same. I think they look like they're exactly the same. You could actually just leave that out and just have the standard one. You would often use a small one if you wanted to nuance something and display something differently. You can add, using RRD tool, you're drawing a graph here and you're adding all of the legend to the bottom and formatting it all. So you might end up with a very detailed standard one, but you might just want a very brief summary one for the the NMIS GUI where you're looking at it. Let's jump on to RRD tool. That's good. Right, adding a system section. So there's two types of data. You have singleton data and you have table data or multiple data. So looking at a human has two arms, two legs. If you're a Time Lord, you've got two hearts, but most humans only have a single heart that I'm aware of. I guess there's some people out there might have two hearts, but normally speaking, there's two eyes, one heart, two lungs, and so forth. So if I was doing an SNMP MIB for a human, I'd be doing for body temperature, I'd have one temperature, right? And I would have another metric, maybe liters drunk. So that'd be one metric that'd be in the system section. So that's a singleton. There's one value that can exist. If I was doing lung capacity, I might do lung capacity for my left and right lung. So I would be using a table of data, and I would have a table describing, the properties of a lung, and I would have left lung and capacity is 1 liter and right lung capacity is 1 liter, right? So that would be how I would model that data. So when we talk about a system section, we're talking about objects that can only be one value for. So, when I'm getting, I may have in a server, I may have memory, but I can only ultimately have one free memory, right? I may have a multi-service system doing whatever. At the end of the day, I can only have one lot of memory that I'm reporting on. If I'm doing some sort of a distributed system like a Cisco device, I could actually have multiple memories reported, which always just confuses people. But, net result is you have a system section for simple objects where there's a single value, or you use the system health section. We're going to cover that in a second. So we now want to go model something, so some big concept. So in this example, we're going to do the TCP. So the system section is for flat objects. So I only have one set of counters for those TCP things. I'm collecting the data for TCP, active opens, passive opens, and so on, input segments, input errors, and so on. I'm collecting all of that data, and I'm keeping that available, and there's just one lot of counters for that. So what is in that system section? So we've actually already included this. This was modeled years ago. So that the TCP is included in the. You can go look at this and have a look. But what is the implementation decisions? What data to collect? You look at the MIB. You do some walks. I found out which MIBs were interesting. So I went through then and I did the MIB name was going to be called TCP. Decided the collection would also be called TCP. I then went and made some more decisions and then added. I added the required MIBs to the model section. I added the new TCP section. I updated the common heading. I updated the common database, and then I added the required graphs into the right place. So let's now talk about counters and gauges. So what does the MIB look like? So the MIB looks like this. So I have passive opens, active opens, and so forth. Now, counters and gauges are very important. And the best description, I think, or analogy for this is to think about your car when you're driving a car. When I'm driving the car, I'm going to drive from Brisbane to the Gold Coast, which I've only done, I don't know, 1,000 times, something like that in the last 10 years. So if I'm driving to the Gold Coast, I'm going to look at the speedo. And I've got other gauges. I'm sitting in my car now. I've got a speedo, I've got a tacho, and they're gauges. And then I've got a fuel gauge, and then I've got an odometer. Now, an odometer is a counter. It's counting how many kilometers I've traveled. So when I start driving, it starts at a number, whatever that number is, 1,000 kilometers. And when I get to the Gold Coast, it's 1,080 kilometers. I've added 80 kilometers. So I've got several ways now I could calculate my speed. While I'm driving, I can observe and I can look at the speedo. And it tells me I'm doing 100 kilometers an hour in the 100 kilometer an hour zone. And then when I get to the 60 zone, I'm doing 60 kilometers an hour. But maybe I glance down, I'm doing 62 kilometers an hour, and I have to ease up off the speed because I'm going too fast. I might get a ticket, probably not at 62, but I might get a ticket. So every time I look at the gauge is what I observe the gauge to be saying. Now, if I left for the Gold Coast, I actually have to go to the Gold Coast this afternoon, which is why it's a good analogy. So if I have to, I've got to get down to Griffith campus. So I've got to go to the Gold Coast. So I'm going to get in the car, and the time is 2 o'clock in the afternoon, and I'm going to drive to the Gold Coast to the campus, and it's going to be, let's just call it 80 kilometers. And let's say it takes me 1 hour to keep the math simple. While I'm driving, I'm looking at my gauge, and I'm doing 40 kilometers an hour around the suburbs, and I'm doing 60 kilometers an hour on the local roads. Then I get to the freeway and I'm doing 100, then there's 110 zone. So every time I look at the gauge, the speedo is doing all these crazy gauges. Now, if I was to sample that and take an observation every minute of that and just write it down, and then when I got to the Gold Coast, then I averaged all of those, I'd come up with some number, and it might be representative, but it probably wouldn't be, right? It might be okay, except that for a whole bunch of time, I'm sitting at 40, and the classic would be if I had a lot of lights, if I was stopped at the lights, right? If I stopped at the lights, I'd be 0. And then if I was accelerating from the lights, I'd be, 40, and then I get to 60. So every time I look at it, it could be a different number. But if I started that timer at 2 p.m. and I drove 80 kilometers and I got to the Gold Coast in 1 hour, and keeping the math simple, that means I've traveled 80 kilometers in 60 minutes, which is an average speed of 80 kilometers an hour. That is absolutely precise. That is irrefutable. The average speed of my travel was 80 kilometers an hour. I can't get a better way to do those calculations than using a counter. So a lot of people go to gauges because they're simple and they're useful. And for certain metrics, like, for example, temperature, that don't change a lot, gauges are awesome, right? So gauges can be really good measures for certain things. Where things can be changing wildly, they're not so good. So we want to use counters, and then we can then determine or extract. We can transform the data and extrapolate how many things happened during that time. So as I was just describing with driving, so now instead of looking at the gauge the speedo every 5 minutes, I could just take a measure of the counter and the time I traveled. So in that 5-minute period, I traveled 5 kilometers. In the next 5-minute period, I traveled 8 kilometers. I could write those down, and I could actually really accurately calculate the average speed of the entire trip, along with the average speed for each 5-minute segment of my drive. Right. So again, having counters is great. It's very usable, and using RID tool that's handled natively for you, you just tell it it's a counter. So what does the TCP MIB look like now that we've just gone through counters and gauges? Very important concept. You can't escape it in data when you're dealing with this kind of data. So, it's telling us that all these things are counters and that this one here is a gauge. All the rest of them are counters. So really nice MIB to use. So now I go in and I would put into my modeling that all of these things are, I would have an option saying that's a counter, that's a counter, that's a gauge. And I've got here my upper and minimum value and maximum value. So I was doing some kind of bounding, or I didn't want it to exceed a certain value. I could use the U, or U is unbounded, but I could put 100 in there if it was a CPU load. I'm never expecting it to be more than 100, and then the system would handle that. Normally, you just use O and U, and you don't have to worry about it. So again, OIDs could be something in the NMIS systems, or you could put an OID in there. So this is the model that we created at the time, a long time ago, for TCP. And then I would go and add any required sections to the MIBs, which was done. Again, don't have to do that again because it's already been done. And now I added to common heading, I added those. So today these would get done in the NMIS9 graph. I definitely need to go to the common database and add a new thing to say I'm going to store data for TCP. So the names here all match. So I'm going to have a new entry for TCP. I'm going to have something called nodes, and the variable name is node, $node, and then health, and then TCP RID. So if the route is called new Asgard, I'm going to have nodes, new Asgard health, a file called nodes, new Asgard health, TCP to RID. And then, you can have more variables there if you want them, if you needed to. And then I'm going to go define a graph for that. And this one was a little bit, funky. So I did some operations here. I decided that the things should be above and below the line. So I wanted to show, TCP input and output. So we show input and output above and below the line. Nice visualization. So, you just push -1 and you multiply them together to get something below the line. And then I just go and print all of that out. So RID itself is a very, very powerful system, as we covered off briefly before. Again, usually when you're graphing something, there's so many things graphed and so many examples there. You just sort of go with the examples that are there. And very good documentation for RID. So now that's us doing a system section. So now we can go through and we can look at a system health section. So the system health section here is how we would do something that's a more complex data structure. So the one I've got here as an example is disk IO table. So while a server can only have one set of TCP connections at a time, it can have multiple disks and be reporting on all sorts of things for that multiple disks, right? So I've got, obviously, I could have, well, most servers would have multiple disks in them. And now I can report on the different, is it full, how much traffic went through, etc., how many blocks were written to the drive. All of that can be reported per disk, right? So this one I've got disk IO table is already been added. You can go review this modeling in ModelNet SNMP, and what the decisions do I have to make. So I'm going to call the thing disk IO table because the MIB name was pretty good and it made sense. So I'm just going to call it the same name. Today, maybe if I was naming it, I might just call it, I might actually call it something just to make it look nicer in the GUI. I might call it disk IO table or something like that. But, nothing wrong with that actual sort of name that's come out of the MIBs. So we'll need to make the following changes. We'll need to add a new system health section to the model file. We'll need to add the required MIBs to the NMIS OIDs. We need to add a common heading. We need to add a common database. And then we're not going to go and make the graphs that we need. and then we're going to add a new section to the header, and we'll show all of this in a second. So I go get the MIB, I have a look at it, I understand how it works. I've got some basic data there. So anything that's an integer is going to be well, that's just going to be not a gauge at all. That's just an index. So always going to have an index with a systemHealth thing. So this is one disk from the systemHealth walk. And I've got these device names, that's called SDA. I've got a read and a written, and I've also got down here a 64-bit counter, because of course, when you get to larger disks or modern computers, they can write so much data. So let's do a quick thing on 32-bit versus 64-bit. Almost everything we do today is 64-bit. However, when I want to store 64 bits in a computer, it's still using a lot of storage, a lot of space at that lower level. For those who don't really think about it, you know, although we might be writing in Python or Perl or Java or something or other, the computers are still storing things in binary, right? So when we store data and we do things, we still have to store something in binary. So we can save a lot of storage by using smaller numbers and storing in smaller numbers. However, they're less precise. So, you know, you'll see now for when we're dealing with certain objects, we just need 64-bit numbers. We just have to use 64-bit numbers. We don't have a choice. You just have to use them. They're more, you run out of space at about 4 billion. 32 bits will get you to about 4 billion. If it's signed, it'll be less. So, you know, you've got basically, you can't store very large numbers in a counter 32 or in a 32-bit number. And that's why we, you know, the maximum size of a disk on a 32-bit system was 3 gigabytes or something like that. So, you know, if you want to have large storage, large numbers, you must be using 64-bit, right? So that's just the way it is. So wherever you can, you should be trying to use 64-bit numbers, but they do use up more disk storage because the actual numbers are larger to store. Now we go into the disk IO section. We're going to add a new systemHealth section. We've added this one called sections, disk IO table, and that's telling the modeling system there's a section down here called disk IO table, and I want you to collect data from it. And we use this in the model policy and other things that we do, but the sections is a way to sort of give you some control over what's being collected as well. So sys has a section. This is where we do discovery. So this is kind of important now, especially important concept when we talk about systemHealth. So when I run an NMIS update, and this was called an update a long time ago because that's what I decided to call it when I wrote NMIS, you know, whenever it was ago. Maybe if I was writing it today, I'd call it discovery, but it doesn't really matter. I'm updating the information I have stored about this device. I'm updating. I'm actually performing a discovery, but I'm updating the data that I know about this device. So that's why it's called an update. So when I'm doing an update, I use the sys section of modeling. And the sys section is also used by the GUI to know what headers to display and to know what titles to call things and so forth. So the sys section is the thing I use to collect data and to discover what the device supports. So I'm going to have an indexed thing, and I'm going to have the headers that I want to display and other things in there. And then in the RRD section, I'm going to be what I collect on a collect. So when I run a collect or a poll, I'm going to go and I'm going to look up this part of the model, and I'm going to go, right, got to get disk IO data. Right, I'm going to go filter things out using this control. So I don't only want things that are called SDA, SR, and disk. And I'm going to generate these graphs, and I'm going to collect these MIBs. That's what I'm going to collect. And the result of that SNMP collection will be stored into RRD if it's numeric. So, you know, the RRD sections are then used to store everything in. So that's it's really important. Sys section for a discovery, and then RRD section for an update, for a collect, a poll. So now I go back into that sys section. I've got the indexed name, and that has to resolve because I'm not using an OID. I'm resolving that. So all those OIDs have to be put into the NMIS MIBs. Then I've got the SNMP sections. I've got a thing here called index, and I'm calling it the IO device index. I've got something else called the device, and I'm calling it the IO device name. And then I've got some other things that I had in that section. And the title is used by the GUI to display that title in the heading. Then we go down to the RRD section. So I've determined that I needed a control on this, so I wasn't collecting other crazy devices. I'm telling it that it is an index section. So I'm going to be looking for an index that's, or I'm going to go use the index that I found, and then I'm going to go and collect these. Now these titles are actually redundant. They don't need to be there. There's no harm in their being there, but no one uses them. So you can use them for documentation. You can use it however you like. You can actually put other arbitrary names into here if you wanted to use them, but they're not. These aren't used. It's not a problem. Now disk.io read X, that's the 64-bit counter. I'm telling the system it's a counter, and away we go. So this is now the data I'm going to collect on a collect, and there's other variables down here. If they're there or not, we've just trimmed them out. And I've gone away and added any entries I needed to the OIDs, so that I've done that up to date, so that I've got anything I need for that MIB. And a lot of standard MIBs, you'll never have to do that for standard MIBs. We've done probably, I don't know exactly how many entries, I haven't counted lately, but there's over 10,000 OIDs that are useful that we've already put in there. So now we've gone and we've done this common heading, and now we go on to the disk.io table for the database. So we're adding the entry for database. Now this one's important because I need to give it an index. I'm going to have multiple disks, and I'm going to store them here in a file, in the directory, it'll be the NMIS database directory, nodes, node name. Then I'm going to put in health, and it's going to start with disk.io table, and then it's going to have an index number. Whatever the index number was in the MIB is going to be the index number of the file on the disk, and that makes it unique. NMIS remembers that relationship and knows where to look up that data and where to display that data. So now I've got to go create a graph. Again, graph's already been created. You can go have a look. This was a pretty straightforward graph. Nothing really too exciting about the graph. We just want to get the data out and display it. Again, RRDs, as we get that data and we pull it out, it's looking it up. It says it's a counter. It does all the deltas for you, does all that maths for you automatically, and just displays the actual, the things per second, right? It's always translating things to per second. And the next bit is we've got to tell the section, and we did show this earlier, but you've got to go tell the NMIS model that it's using sections disk.io table. So if you don't do that, it will not load this. It won't know. You can go have the actual modeling present in the files, but unless you go and tell it to use that section, it won't use that section. And in the end, now you have a systemHealth section in the NMIS GUI, and you have the everything modeled. So you have a list of the disks, the IO device name, and then the history of those disks. In this particular MIB is actually the bytes that have been written and read, and then also the blocks, which is the IOPS. So that's actually the IOPS of that server shown on the right. Cool. Now we're going okay for time, and there's going to be time for some questions at the end, I'm really hoping. So let's just keep pressing on. Device model plugins. If you're not comfortable with code and things like that, just don't use a plugin. But plugins are there to solve all those crazy problems that you can end up with. So when you abstract systems, you end up with this sort of interesting conundrum that you can go write a language to go and abstract something, and then you keep abstracting it. And at some point you have this description language, the modeling system, you have this description language, and now you just got to start dealing with all of these corner cases. And you make a decision at that point. Am I just going to keep extending my model description language? Am I going to keep just adding functionality to that and keeping the engine up to date? Or is there some other way that we could do this in a more scalable way? And this is one of those architectural sort of decisions. So we made the decision a long time ago that NMIS should support a plug-in system instead of continually extending the modeling system and updating the engine and creating essentially less flexibility than was needed. We wanted the modeling system especially to be that you didn't need a developer, you didn't need an NMIS developer to extend NMIS. Now the reason for that is that I'd spent many years at night, adding code into NMIS early versions for people, and that wasn't a scalable solution, right? So other people then learn how to do that, but then there was like 20 or 30 people who used to do it, still not scalable, right? So So basically, when NMIS8 was reinvented, and Eric Greenwood was doing the architecture of NMIS8, or what became NMIS8, he it was determined very early that we needed a modeling abstraction system, and then we quickly found out, when we were doing NMIS8 and the first couple of customers came along, there was just all these corner cases that we had to deal with. So we made that architectural decision that instead of trying to keep extending the modeling system, and we did a bunch of extensions of the modeling system, handling crazy things that devices do. And then I kind of felt that we got to the most of them at that point. I said, right, that's enough now. Now, it might be that we might add a couple more features to the modeling system. There's a few plugins that we use for data association. It might be nice to have the modeling system handle that automatically, or have a way to express that in the modeling system. But basically, plugins are there to handle crazy things that vendors do with data and MIBs and so forth. And also, it's the extension point so that you can use any protocol at all that you want to collect with. So we've had customers use, as I mentioned before, netconf. You can use opconfig to collect data from Linux servers or Cisco routers or whatever, Linux Juniper devices, whatever you want to do. You can have you can use RESTful APIs to collect data and put it in. You can do just about anything you want using a plugin. And that means that the plugins are, essentially infinitely extensible, infinitely open, and much more flexible. You don't need someone on the NMIS development team to do those. You can do them yourself. They're fully supported. You've got a way of interacting with the system. So that's why they exist. And you have 4 types of plugins. They can all exist in the same thing, but the 4 ways that a plugin will run. The plugin will run after an update. So when you run a node update, the plugin will run after the node update. All the other things have been done. Or you can run one after a collect, or you can do it after all nodes do an update or a collect. Most of the time, most plugins are probably your update plugins, and then you just get the data in the right place for NMIS to do its job. And then, we do have collect plugins for various things for people solving various problems. So you can use it to manipulate already collected data. Like we had a nice plugin written for multiprocessor CPU devices. So we sort of go and take the 10 CPUs that might be on a server, and we go and calculate the average CPU, for all those 10 CPUs. So you have a single metric for a Windows server for CPU. Now, because Windows doesn't have a MIB for that, we created the instrumentation for that using a plugin. Right? And we did some nice maths where we actually calculate the average CPU, but we also store the maximum value of the CPU for the time. So that means you kind of got, so if you have a single, single crazy core, like a hung thread that's just smashing a single CPU core, then you can detect that as well. So we sort of put those metrics in, as an example of manipulating existing data. And you could also go and collect data using whatever you wanted to do. You can save data into the performance database. You can save data into the inventory database. You can save data to files. You can pretty much do whatever you want to do in an NMIS plugin. And it really is there to ultimately just handle all the crazy corner cases that manufacturers don't solve themselves or leave us with, the vendors, when they make these things. Or it's to do, something that data normalization, associations, all sorts of little things. You don't need, generally speaking, you don't have to write plugins very often, but they exist so that you can solve the problems that you might need to solve. And there's many, many examples. Never ever start from scratch. There's some good documentation, and it's we'll talk about how to troubleshoot them in a minute when you're sort of running your environment. Model policies were added into NMIS some time ago. We kept adding all of these features and capabilities into the models, and we said, oh, well, our service provider customers will want all of that MPLS data collected and probably all that QoS data collected, but our enterprise customers probably don't want all of that MPLS data collected. So we solved that by having a model policy. So we turn, using the model policy, you can disable the modeling parts of the modeling system without having to go and touch all the files. Right? Obviously, you can disable modeling by removing files, but that becomes a nightmare for maintaining files and doing stuff. So we built the modeling system. It's quite simple, but very powerful. And you can basically tell it what things to turn off. So by default, a bunch of the MPLS stuff is turned off. And then that means that the modeling system, unless you care about MPLS, you don't want to turn it on because it's so much data. And then so for all those devices that support MPLS, you'll be collecting all this extra data you're not going to do anything with. So that's why the modeling policy system exists. It's quite simple, it's quite powerful, well documented, and it's got some other nice features that you can leverage with it. But it's out of the box functionality is to disable modeling that you don't want. So thresholding is our next big topic. So there's a lot of thresholding already done, and there's a feature that we've just adding. It's about to be released, where we're going to be leveraging the thresholding system to solve that problem. But we're adding the ability for some mapping. So on our maps at the moment, you can have interface lines. We had a customer who wanted to have the signal strength of a radios, because they're using radios. Would make sense for the signal strength of a fiber as well, like optical fiber network. You might want to have the packet loss or noise to signal ratio or something or other that you want to have on a map, and then you want that to be a heat map. So you want to be able to step back. So when it's bad, you want the line to be red, and when it's good, you want the line to be green. So that sort of conceptual thing. That's what the thresholding system is there for, and that mapping feature is going to make use of the thresholding data. So what you do in NMIS is the modeling system knows how to talk to all the different components. It knows how to get all the data out that it needs. And then NMIS can ask it these questions, get the performance data out right now and say, does it exceed this threshold or not? So let's go through how that sort of works. And that's your checklist for what needs to happen. So you do have to think about what it is that you want to threshold and why you want to do it, and is it useful? I've seen people add thresholds for things and then later disable them because it was not useful. So you do want to think through, why am I thresholding this? What purpose does it have? Like, it's a proactive event. I'm going to generate a proactive event. What do I expect the humans to do when they get a proactive event? Because if you're just going to make a whole bunch of proactive events and send them to the humans and don't tell the humans when the temperature goes high, pour water on it. Like, if you don't sort of inform the humans what to do, when the temperature's high, or they don't know, then it might not be so useful to add. Something like proactive temperature means, hey, the air conditioning's gone, go fix the air conditioning. That one's kind of maybe self-evident, but like when you're thinking about what those thresholds are, they're going to be these proactive events. And there's a session I did a couple of weeks ago about the difference between reactive and proactive. Proactive is incredibly important, and you should do it, and you should be proactive, and that's what thresholds are about, right? But they're not necessarily, you don't need someone to look at the problem now. You're just bringing it to people's attention that the temperature's high, and they might want to go fix the air conditioning unit before the temperature gets critical. So what is the thing you want to do, and is it useful and meaningful? Now you're going to give it the name proactive. So we're going to go through a temperature one in our example here. So we've got something that's called environmental temperature, and it's an indexed thing in systemHealth, and it's got a threshold, and we're going to give it a threshold called environmental temperature, env-temp. So this name, these happen to be all the same names, that's okay, but these names need to match. So I'm going to go into systemHealth into something called env-temp. I'm going to have a threshold called env-temp. So now I go to inside the thresholding definition, I'm going to go to common threshold. I'm going to add a new section called env-temp. And when the modeling system, when NMIS looks up this, it's going to load this data here, right? So I'm looking for an item called current temp, and that's the value that I'm going to be evaluating. That's the item that I'm looking for, is current temp. And the event I'm going to generate is proactive temp. And there's my threshold. So the default values I'm going to threshold against are warning at 50 degrees, assuming this is degrees Celsius, minor at 60 degrees, 70, critical, so forth, up to fatal at 90. And then I need to add a section to the stats section. And again, these names need to match. So the threshold env-temp is going to be that name, but this env-temp here is actually matching the name here, because I'm going to do a data extraction from that database. I'm going to get this, I'm going to load that env-temp database. I'm going to get out current temp, the variable called current temp. I'm just going to call it current temp, but I could rename it here. I could call it anything I want. And then I'm going to print out current temp, and the thresholding system is going to get that data and use that as the value to evaluate with these thresholds. So, Relatively straightforward. I've got abstractions in place so I can do cool things. So if, for example, I had a whole bunch of different things doing temperature, I could actually normalize this whole system and have one set of temperature thresholds for many, many different vendors. So you can use the thresholding system to normalize and update names of things and give things different names. So how to run thresholds manually. So when you if you want to test a threshold, you now would go and change it to some value. So you know the temperature's over 5 degrees. It must be not turned on if it's 5 degrees. Maybe it's in my back garden at the moment if it's 5 degrees. It's not that cold out there, but it's pretty cold. So I'd go run this CLI command. We're going to talk about the shell in just a minute, but I'd go run that command, and then I would go look up this file, and I'd have the collect data, and I would look at the debugs, and I'd find out if the threshold had fired or not, right? So that's how I would test the thresholds. I would set the threshold to be 5. I would have to, then I would run the thresholds, and then I would check it. And then when I want to clear the event, and of course an event would be generated, you go look at the GUI, there'll be an event for that device, morning proactive temperature, for device, etc. You'd have that exist, and that would be in the system. So now we go to some advanced things that you might want to do, and controls are very powerful. So now what you can do is you might say, well, I want my devices with certain names, or devices that are Cisco devices have different temperature ranges, or maybe things in the data center. That data center runs hot. We want the temperature raised differently there. So you would use a control, and you would have selects, and you have multiple selects. So when my role type matches core, I use that set of thresholds there. And this is how I would tune my thresholds. So in the example here, this is proactive CPU. So for core devices, I've lowered the thresholds. For the default values, they're a bit higher, and that's okay. So if I don't match a control, I use the default values. So you should always have a set of default values, and you can do, there's lots and lots of things that you can do with controls. We've added, I don't know that we've actually added any for a while now, but there's lots, there's heaps and heaps and heaps that you can use for the controls. If there's one missing, please let the team know. But all the normal things that we'd expect that you want to do are available there. Cool. Custom alerting. So what's the difference between alerting and thresholding? So thresholding, what is important, I forgot to mention, the thresholding system, inherently in thresholding or doing this kind of performance management, you want to dampen down things. So you don't care if your CPU spikes to 50% for like a second or a minute. You're not really worried. If it stays at 50% utilization for a long period of time, maybe 5 or 10 minutes, then you might be worried about it. But what I hear people describe is too much noise. So what NMIS has got, and when they come to our system, when they come to NMIS, they find they don't get as much noise as some of our competitor systems generate, because we use a dampening mechanism, and by default it's 15 minutes. And this is really nice. So that CPU, to be above a 50% threshold, that means I have to be over 50% for 15 minutes or more, right? All of this is configurable. You've got quite a lot of granularity, but the default is 15 minutes. So that means my interface utilization might go to 100% for 5 or 10 minutes, but the average for 15 minutes might be 45%, depending on the exact maths and the exact things going on. Or it might go to, I might have my threshold set for my CPU to be that 50%, but I might want to do it for an hour. So I'm not worried about that. I probably wouldn't do that for CPU, but I might do that for interfaces. I'm not worried, if they're doing downloads and backups and it takes over an hour, that's okay. But I don't want to be bothered. If it's going for more than an hour, I want to know about it, right? So the thresholding system inherently has dampening. You can just disable it using what's called the threshold periods. You can just set them to the default to 5, and it'll just be 5 minutes, the last thing collected. But I would advise against that, and I would advise even for looking for longer thresholds for certain things, because when sort of people say to me, "Oh, it's too noisy," well, the things are happening. It's detecting things. If it's too noisy, then maybe you just don't need to know yet, right? You want to know when the interface utilization has been high for 30 minutes, not for 15 minutes, right? And that might be more useful. So that's the threshold period system. There's a whole lot of documentation on that. So let's go back to alerts. So custom alerting was added for this thing is broken now, I'm alerting you. So fan failure, maybe a temperature thing, instead of doing it, you don't want to dampen temperature. If that temperature goes over 75 degrees, then I just need to know right now, right? I don't want to dampen it. I don't care about any mass. I don't care about what, I just want, tell me now. So this is reactive. So you could consider that your thresholding system is proactive, where your alerting system is reactive. Tell a human now, the human needs to take action on this now, right? So your alerting system is there to detect status of things failing. So maybe you've got an IPSLA probe that's failed, you've got a temperature that's gone too high, you've got a fan that's failed, maybe you've failed over a redundant pair of firewalls and you detected the firewall failed over. So that's what custom alerting is about. It's all been documented, and it's quite a few examples written up. The main thing to do with alerts that probably catches people out is you have two types of alerts. You have the simple alerts for that system modeling, so where you just have a singleton value in the system, you have those kind of alerts, and then you have alerts that are used for the system health modeling, and that's your main difference, and they're in different structures in the modeling system. So you'll sort of see examples of those in the modeling system, and it's really well documented on that page. And just to make sure that you're not confused, but it might confuse you if I don't mention it, you can just evaluate and test, is this value above or below this number? Is it on or off, right? You can do all sorts of evaluations of the values that you're collecting. So it's not just numerical, you can do text evaluations. Maybe SNMP poll returns the value of failed. So you want to say, if this value is failed, raise an alert, right? You can do that. But if you're using temperature, or maybe you're doing something with voltage or something or other, you can apply a threshold and have the criticality be variable. So when you do a normal test and you're just saying this thing failed, you would have the level set to warning, critical, fatal, whatever you decide, one single possible value. When you use a thresholding stanza, the thresholding little bit in the alerting, you can actually do a comparison. So if it's above 50 degrees Celsius, and it starts in reverse order. So if it's fatal at 90 degrees Celsius, or it's critical at 80 degrees and so forth. So when it does the evaluation, it says this is critical, and the alarm, the event generated by NMIS is critical, and that goes right through. So you can have that. You can you're still comparing. You're crossing a simple threshold that's above the base number, but now it's going to raise the criticality depending how far above that number it is. So very simple but very useful feature for knowing, if it's critical, I need to act now. If it's warning, I'm gonna wait. I'm gonna keep an eye on it for a while and see what happens. Okay, so running and thresholding. So running and troubleshooting. So let's introduce the Linux shell. We had a Linux shell in NMIS 8, and so we've done a little bit of work. It's experimental. It works fine. I mean, I just tweak away at it and add things to it because I use it all the time. So I don't know if anyone remembers things called time and motion studies, but people who use computers should think about time and motion studies. Command lines are fast. GUIs can be fast, can be slow. So that depends on all sorts of different things. But when you have to go and type great big long commands in, it can take you time and you don't remember the syntax. But having that nuanced ability to have all those options and variable things and different things are very useful, right? So you might need more nuanced commands at certain times, but the NMIS shell is there to be more efficient so that when you're running common things that you're doing all the time, they're just summarized into the NMIS shell. So you can go into the NMIS shell. To install it, you just do a symbolic link to somewhere in your path. So for example, that command there, and then now you can see the shell. We'll go have a quick look at this in a second. And now you can go run a collect with the debug, and now you've got the debug running. So this is very fast, easy to remember, and fast to run, and it automatically does a bunch of options for you and takes care of a bunch of things, so you don't have to worry about the NMIS CLI. So I'm just going to go NMIS, it's installed. I'm going to go, and I can restart the daemon, I can fix perms, I can do all sorts of different things that I might want to do. But I now go, oh, there's a nice one here. I can get the Unix time from a epoch, right? So I can do whatever I want to do. Things that I spend time doing, I've put into the shell over time because it saves me time and motion. So NMIS, we're going to operate on new Asgard. That's a router. I'm going to do a collect, and I'm going to do a debug 3. It's now gone off and it's run the scheduler, and I've now got a job. So now I can actually go NMIS schedules, and it will tell me what's in the schedules. There's actually nothing. It's already finished. So now I can go ls-lrt/temp/new. Oops. And there's a file from the debug. I can now go look at that debug. I could use anything I like, but I'm using more. So now if I want to go looking at the thresholding, it's loaded common threshold. It's processing threshold response. So now we and it says here, starting thresholding for node new Asgard, and now it runs through all of those thresholds and tells us what it's doing. I've set it at verbose 3. Verbose 9 is very, very verbose. I'm typically debugging things at verbosity 3 or verbosity 5. Usually by the time I'm asked to help out with it, I'm usually after the verbosity 5. I find 9 just too verbose. And it tells you what it's doing, right? So the debugs in our system are telling you what you're doing. I grew up making Cisco routers work, and without debugging Cisco routers, I don't think anyone would be successful. So having an interactive debug tool is very, very powerful. So something I learned early in my life, in my career. So we have debug, all through our products, so that it's easy to debug and understand what's going on. It's easy so when I encourage the development team, if you're using a debug in development to get the feature working, just leave it there and make it a higher verbosity level so that you can access that debug later, or our customers can access that debug to understand what's going on. So you'll find lots of debugs across our products. And NMIS9, we revamped all the debugs so you can actually enable it across all the daemons and do all sorts of cool things with it. But interactively, there's a quick way to run it with the NMIS shell. And now you can access that collect. You can see what's going on with your modeling. You can see what's going on with your thresholding, and you're just saving a bit of time, because this command is much, much easier to remember than trying to remember the full syntax for the NMIS CLI. Here's the full syntax for the NMIS CLI. So if you needed to run an update and you wanted full verbosity, then you would do this command here. You would go NMIS CLI, act schedule, job type update. Job.node is localhost, job.verbosity 3, job force equals true, job output equals that. So when I ran that command there with NMIS collect debug 3. And again, you can use the shell. This is your full syntax, so you might need to use this to do something really, some advanced feature or something advanced. That's great. You've got the ability to do it here. You should also just keep an eye on that scheduler when a server's getting busy. If you're doing a test, I find a lot of people, when they're sometimes using a test server, they add a couple of nodes to their test dev environment, and then they sort of don't keep an eye on it well. And sometimes their test dev environment's misbehaving. Their production environment's working perfectly, but they maybe not have enough resources on their test dev environment. They delete a couple of nodes or tidy it up, and all of a sudden everything works better. But sometimes when you're doing a lot of this interactive stuff, just keep an eye on that scheduler, make sure the jobs are getting done. So if you want to run debugging on a device model, so if you're doing modeling, you'll get a lot of really good information as you go, and you'll see that information come through. And typically you want to look for this update RRD. So let's go back to that debug that we just did, and we'll go have a look at that. So now we've gone through the system, we've been collecting things, and it now goes to the update RRD, and it's going to go down here, and there's our actual update there. So it says here, so there's the update RRD section started, and it says I've got this node, I've got this data, and now I'm getting this data store buffer element hit. So these are the variables I'm storing, and these are the values that I'm going to store them in. Right. So that's really useful. If I'm doing that, I'm storing data. And you can see, when you see NMIS sort of collecting, it just collects lots of these really, 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 really fast. A debug 1 is actually often enough, but when you just want to see what's going on, you can just do a debug 1, which is just debug. What's always important, and I remind people all the time, is much less verbose. It's like a tenth of the logging. So I'll go have a look. And there's a couple of things here I'll just bring to your attention. So at the bottom of the line here, it says completed job, collect, removing from queue. That means I've completed and I've, sounds obvious, but read the words, right? So what does it mean? I completed the job, I've typed collect, I'm removing it from the queue. And then you'll probably want to look up immediately above it and say, well, what was I doing? I was collecting for this node, New Asgard, and it took 6 seconds. That's okay. And then you can, the poll time recorded for this was actually 5.9. And then I did a final graph reach and so forth. So everything it's doing, it's telling you what it does in even the basic verbosity. So you can usually then say, well, I need to know what's going on here in more detail, what happened here, and then you could go and run a more verbose debug. Here's the thresholding system running. So I'm thresholding packet errors out. I've got an index of 7. I'm doing packet errors out. I've matched the default entry. I'm now doing the item name if out errors proc, and the value is 0. So my result of my threshold is normal, right? So this is how you would, if you're updating and tuning your thresholds, you would then go and use this to debug and make sure that it's working the way you want it to. Or if it's not working the way you want it to, you could look at what the device might be doing that's crazy, or what in your thresholding you can tune. So all of this just goes back. So we've got some buffer things done here for different thresholds. There's lots and lots of things on this particular device. And then we go create update RRD, it's finding that, and then it wanted section this, and then it wrote this, and create RRD update. So it tells you what it's doing all the time. And if you're not sure what's going on, you just go to the next level of verbosity and find that section. It's not written in Portuguese or Spanish or whatever. It's written in developerese. It's a sort of a language that most humans speak. Not everyone can understand, but it's just written in a if you're working on these things, it should make sense. I wouldn't say it's purely development language. The debug's out. It's definitely to do with network data collection and collecting things and where it's been written to. So it should sort of make sense, most of it, what's going on. Cool. Let's go back to our slides. And because it's the second time I've delivered this, I've managed to get through it right on time. And this is our questions. So we've finished early. We've got 15 minutes scheduled left. If there's any questions at all, we can open up, and I'm happy to demonstrate something, show something, whatever we want to do. We've got a lot of time left.
And can you dig a little bit about the alerts? You said you have 2 different parts of the alerts, and you have the article. Can you?
Yeah, let's go have a look. Okay. All right. So you have basic alerts, and then you have more advanced alerts. So that's, and you use a basic alert. It describes these tests that you can do, and they're quite, they're meant to be numerical, whereas you can operate on strings. So you can do greater than, less than with strings, and you can do mathematical ones. So you can do, these are Perl expressions, so you can basically do quite useful things. So where to add the alerts, if you're doing something to do with TCP, so we did that TCP modeling before. If I wanted a count, if I saw that my TCP established sessions was above 200, which is quite a lot for a small server, not a lot for a big server. So if I wanted to do a test, R is my value. So I'm going to compare R against 250, and I'm going to generate the event high TCP connection count. Automatically, it will have an alert, the keyword alert put in front of it. Automatically, you don't have to worry about that. And then level will be warning, right? And that's in the section system, sys, and then alerts. So that's where that is dealing with things in the system section. These alerts work on the system section. Very important. right? So if the structure shows the alert under the system section, it's only dealing with data in the system section. And a very subtle thing, you can actually, this will actually go and poll new data for you. So this particular, the way this particular thing works is it will go and it will get extra data if you needed it to, because we don't assume at that point that the data that you do or don't have that captured already. So we just said, well, let's just go get it again. And it means that it's the data's hot and live and ready to go. And that's what we do with that alert section. Now, we've got some examples there, but let's jump down. So if I wanted to do a serial number, and serial number's invalid, right? So if I had some dodgy serial number, I could do a regular expression or something and serial number's invalid. Now, the more advanced alerts are at the high level area. So I have alerts, and then I have something in the section services, and then I have high process memory usage, right? So it has to be for system health modeling. If I'm doing something, this was something done with hardware system processors. So this is actually collected from the services. This particular data is collected automatically by NMIS in the services modeling. And then I want to have an alert called high process memory usage. So now I can go and look at this thing here, and if I see it's above whatever that is, 300,000, I can raise an alert, and my unit is kilobytes, and it's going to put all of that together. And this is using a system health section, right? And the subtle difference there is that NMIS has collected the data and saved the data and done a bunch of stuff with it. And then these alerts will use the data that's already been collected because it was collected a second ago, right? Or 2 seconds ago, right? Or half a second ago. So now I collect the data and then I process the alerts for that data. So that's the main difference. So if you're dealing with alerts at that top level, so the same level as common system storage alerts, then they're operating on system health data. If I'm dealing with things at system alerts, then I'm only dealing with things modeled in the system data. Does that make sense?
Yes, it does.
Cool. I think there might be an example of a threshold here. Yeah, here's an example of a thresholds. So normally I would do a test. My type would be test, right? So I'd just be testing, I do a test and I'm evaluating the test. Now, I'll just explain these CVARs. These are variable substitution. So I need to tell NMIS which variables I want to get. So I'm saying, go get me a variable, and I'm going to call that CVAR1, and I call that CVAR1. This is a technique used in when you just don't know, you don't want to hard code all of your variables everywhere. So you don't want to go and have your expressions you don't want to expose all of your variables into these sort of expressions. So this is a way to have NMIS target the data that you want to express and evaluate. So the value that we're going to display in the event is this one, and the test that we're going to perform is we're going to get hardware run host resources, software run perf memory, and we're going to get that value out, and then we're going to compare that value against 300,000, and if it's higher, that test will trigger. It's true, right? So when it's true, the alert is true. When it's false, the alert is false. And that level will be given warning, right? So let's go down to the thresholding one. Same sort of thing. I'm going to go get the value out. I'm not using a test anymore. The test is blank. I'm going to go get the value out. In this case, I've got storage size. This is a disk being full or not. And so I'm doing storage size and storage used. I'm calculating storage utilization by doing some maths. And then I take that value and I compare it to these thresholds. I start at the highest value and it says threshold rising. There's a threshold rising, threshold falling. So sometimes 1 can be bad, sometimes 1's good, right? So in CPU load, 1 is good, 50 is bad. in temperature at the moment. You know, 1's bad and 20's good, right? Maybe. So if you want to get down to 1 degree Celsius, you probably want to go put on extra layers of clothing. If you're, you know, so that's a threshold falling, whereas a threshold rising for temperature in a data center would be bad. So high temperature would be bad. So the value here would now come back as whatever we get the value out, and then it's compared against these numbers in order. And if it's higher than 99, it's fatal. If it's high, but if it's below 99 and higher than 98, it's critical, and so forth. So that's the way the threshold rising is evaluated, and then it results in, if it's under 70 degrees, it's normal, right? So that's how that's evaluated using the thresholding, and that's just alert thresholding, not to be confused with the NMIS thresholding system. And you can get, you know, these values here to get that data out. You can do any maths that you want to do in there if you had to, because we sometimes get people or data stored in weird values, and it's got some sort of signal strength that's in some, you know, decibels or something or other, whatever it is. You can do whatever maths you need to do in these expressions as well, because it's important. Sometimes what a human needs to see to understand it is different to what a computer needs to see to understand it. So the maths might be different to present to a human. So that's the maths you might use in a graph, might be subtly different to get that graph right for a human, versus when you're doing something like this, you don't need to be as you might need to be, you can be more direct with the maths, because you're not showing it to a human directly. You're just evaluating it and then generating an alarm. So subtleties in how you have computers work with humans. Cool. Great question, Gladstone.
Hey, Keith, Tony Bishop. Apologies if this is a dumb question, but I think at the start you said there's multiple ways to collect the data for modeling. We went through the SNMP modeling. I think you mentioned RESTful API. What was the other way?
Oh, WMI. I mean, so by default,
WMI.
NMIS supports WMI and SNMP natively. So you have the ability to just define those, you know, natively. So netconf. So you would use now you're using a plugin, Tony. You can, if you're using a plugin to collect data, you can literally use any protocol on the planet, anything.
Right.
Anything that you can find code for to write. So, you know, we've had, I know there was one customer that did something with Modbus for some reason, whatever it was. Modbus is a building technology, IoT technology. You know, like we've had lots of RESTful APIs. We've had quite a bit of stuff done with opconfig, where you go run a command in opconfig and collect the data. Then the plugin extracts out the data it wants from the command line, and then, you know, saves that into RRD. That was for, we've done that with a couple of things. It might have been temperature on Linux boxes, like older Linux boxes that didn't have it available in SNMP, but you could run a command to get the temperature. So there's a whole bunch of examples. And when you run a plugin, let's go have a really quick look at one. If I can find one super fast. Any other questions while I look for a plugin?
I was going to ask about application modeling of data from BAT, but RESTful APIs and, you know, potentially syntax kind of answers that.
We did one here. Here it is. So F5 had this weird thing going on. This was actually done for our friends at Services Australia. James is here on the call. So these F5s had this weird thing where they didn't like doing what they wanted to do with the number. I won't say the details, but when you got to a certain number of virtual interfaces, virtual IPs on an F5, the SNMP MIBs just weren't coping, and so they were just timing out. So we basically found out, or Simon did the work on this. Doug was helping out, and I helped out a bit. But, you know, basically, we went and got the data, and here's the magic. So you basically went to the F5 and you asked it, you know, the RESTful API, and the data was pretty much the same as the MIB, which makes sense because it's the same data. They're going to report on it 2 different ways. So we basically, where those F5s had, you know, a huge number of virtual IPs, we made up the option to do an API call. So this thing here, you can see here that the API gets the credentials and everything are loaded from a JSON file, so you're not putting any passwords in the code. And then now you set up your, you're just doing your error message handling and so forth in the code. And then down here somewhere, we set up our headers, content type JSON, and then now I do a Mojo get, and that's pretty standard for getting a authentication token, and now using that authentication token to then get data. And there it is there. That's the URL, and we hit that URL and we get the JSON document back. So that's an example of getting back performance data, well, whatever data from RESTful API.
Yep.
And then Louis, your question might be a bit more nuanced, but you can use this method to get any data you want at all. And then we obviously have the services system inside NMIS is another type of data collection that we do. You can use plugins in the services thing as well, and you can do simple plugin. You can do simple service checking, but if depending what problem you're trying to solve, you might solve that using services. Or if you wanted to do something with application monitoring, you could absolutely do something, with modeling and do something in modeling to do something with that application monitoring.
Perfect.
Cool. Feel free, please, if you've got any questions at all. I'm happy to do a follow-up call internally or for customers. So if there, I know there's definitely, I can see James listed, and there seems that there's 29 of us on the call. So if there's anyone on the call who wants a sort of follow-up session, please just reach out. Just drop me an email, and I can set up a follow-up session. I'd want to be answering questions, right? So, if there's some sort of particular topic that you weren't clear on, we want to do a bit of bit of something, let me know. In that material that I showed, those reference links, there's actually a bunch of tutorials available there. Those handy links, there's some tutorials available there, so you can actually go through and there's a tutorial on how to add a threshold, and there's a whole bunch of stuff there that's on our website. But the goal of this call today was to sort of break the ice and to help people get an understanding for it. The modeling system is pretty flexible and pretty powerful and can do almost anything, and with the plugin system it can do anything, so it's pretty cool. And it doesn't require you to be a developer. You obviously have to understand data and understand what's going on. Plugins are a more advanced thing and probably require a bit more developer understanding. But you don't have to be a full-blown developer, you just have to be happy writing some scripts and stuff. And you can go write a plugin stub, and this is important. Some people are more comfortable in Python, so you can write that plugin stub in Perl, and you can actually go run some Python code to get the data for you, and then grab that back as a JSON document, and then just process it back through in Perl. So you don't have to write your plugin purely in Perl. I think Perl's great, but yes, it's an old language used by people who've been working in the industry for more than 5 years. We're now over time, so if anyone's got anything they would like, please let me know. Otherwise, hope this was useful for everyone.